We are covering section 4.1 today. So, section 4.1, this is about inverses. For a function to be invertible, it needs to be one-to-one. So, we need to talk about what is the one-to-one property and what does it mean. This one-to-one property, it only applies to functions. So, you can only apply this to things that have already passed the vertical line test. So, we'll say one-to-one function. So to be we say a function is one-to-one if for elements a and b in the domain of f, a not equals b implies f of a not equal to f of b. So we're going to write that down and then talk about what that means. So we say a function f is one-to-one if for elements, we'll actually need for elements a and b in the domain of f, a not equal to b implies f of a is not equal to f of b. So what this means is that different inputs get different outputs. So this means different inputs return different outputs. So we can't have two inputs, or I guess two inputs can't create the same output. So stated another way, two inputs can't have the same output. And we'd like a nice easy way to check this. And so how we're going to check things is we're going to use what's called the horizontal line test. So the vertical line test tells you guys if the graph is the graph of a function. So if you know the graph of something and every vertical line hits the graph once, then the graph is a function. The horizontal line test, we only apply it to things that have already passed the vertical line test, so we're already sure they're functions. Then we can tell if the function is one-to-one by the horizontal line test. It works exactly how you want it to. We say a function is one-to-one if, so a function is one-to-one if every horizontal line intersects the graph of the function at most once. So if every horizontal line intersects the graph of the function at most once. So basically, if we have a graph, now we can tell if the function is one-to-one, and if the function is a one-to-one, then it is invertible, which means an inverse exists. So the nice property we're going to use for one-to-one functions is once we figure out the function's one-to-one, then we can go ahead and figure out the inverse of it. So real quick example, we'll say which are one-to-one. So we have a diagonal line, we have a parabola, and we have a cubic. So if we look at the diagonal line, every horizontal line hits this once at most. So yes, this is 1-to-1. For the parabola, if I can draw a horizontal line, I found a horizontal line that hit the parabola twice. So no, a parabola is not a 1-to-1 function. This sort of cubic type here, every horizontal line hits it once. So yes, this one is 1-to-1. So as long as the horizontal line hits the graph more than once, it's not 1-to-1. If all the horizontal lines hit the graph only once, then it is 1-to-1. And if it is 1-to-1, then it's invertible, which means an inverse exists. So next up, we're going to say, given a function, how do we find the inverse? And then after we do that, we need to talk about what if we have two functions and we want to check if they're each other's inverse. Then we need to talk a little bit about domain and range and graphing them, and that'll wrap the section up. So let's say given f of x equals x cubed minus 2, we want to find the inverse f inverse of x. We use f to the negative 1 of x to represent inverse if f of x is 1-to-1. So in these, step 1 is check to make sure your function's 1-to-1, or the problem will tell you if the function's 1-to-1. X cubed minus 2 is the basic cubic function shifted down 2 units, so it looks like that. Every horizontal line I can draw on it will only bump that graph once. So yes, this is 1-to-1. So we know that the function's 1-to-1, so now we can figure out an inverse. Here's the process to find an inverse if you're given a function f. Step 1, replace f of x with y, so y equals x cubed minus 2. So I just replace the symbol f of x with y. Next, switch x and y. So now we get x equals y cubed minus 2. And then we solve for y. So when you guys are given a function and you want to find the inverse, replace f of x with y, switch x and y, then solve the result for y. So this negative 2 needs to add back across as a positive 2. And then I need to get rid of the cube. To get rid of the cube, I apply cube root to both sides. Since we're using an odd power to undo an odd root, we don't need the plus or minus. It's only if we're undoing even powers with even roots. So we get y equals cube root of x plus 2. So to wrap up, this is our inverse, and the final step is once you get it there, write it in the inverse notation. F inverse of x in this case is the cube root of x plus 2. So that's the process when you guys are given a function and you're told to find the inverse. Verify it's 1-to-1 first, or the problem may tell you it's 1-to-1, in which case you don't need to verify it if they say it is. Then replace f of x with y, switch the x and the y, solve for y, and then that's your inverse. Let's try one more of these real quick. So let's say we had a line like y equals, or let's say f of x equals 4x plus 3. We know this is a diagonal line, so we know it's 1-to-1. We don't even actually need to graph this one. We just know it's diagonal line. And for a diagonal line, every horizontal line you draw across a diagonal line will only bump into it once. So we know this is a 1-to-1 function. So replace f of x with y. Oh yeah, we should say what we're trying to do. We're trying to find f inverse. So to find f inverse, replace f of x with y, switch the x and the y, solve for y. So the 3 subtracts across, equals 4y. I need to divide everybody by 4 to get the y by itself. So I got x over 4 minus 3 over 4 is my y. That is my inverse, so I write this as f inverse of x equals x over 4 minus 3 over 4, and that's my answer. So if they give you a problem and they ask you guys to find the inverse, verify it's 1-to-1, or the problem should tell you it's 1-to-1, and then replace f of x with y, switch x and y, solve for y. Once you get the y by itself, write it back in the inverse notation. Oh, and if instead of f of x, if they give you a g of x, say, then this would be g inverse of x. So the f would be replaced with the g. Okay, so the next thing we need to talk about is what is the definition of two functions. So instead of being given one function and told to generate the inverse, what if you have two functions and you want to know if they're inverses? So what we check is if we're given two functions, and we want to know if they're inverses, first of all, check and make sure that they're one-to-one functions. If one of the functions is not one-to-one, then it won't have an inverse, so you can just stop right there. But given two functions that are one-to-one, they are inverses if f composed of g of x equals x and g composed of f of x equals x. So if you apply the first function and then the second function, the first function will send x to g of x, the second function will send g of x back to x, and then it has to happen in the reverse order also. F will send x to f of x, and then g sends it back to x. So we basically want to just check these two things. We're also going to say a little bit about the domain and range real quick. There's kind of a neat relationship between these. We get the domain of f is the range of f inverse, and the domain of f inverse is the range of f. So if they're inverses, the domain of f is the range of the inverse, and the range of the inverse is the domain, and then the domain of the inverse is the range of f. So that's a nice little property that these have, is the domain of one is the range of the other. Okay, so let's look at an example with some numbers to kind of see what does this actually look like, and then we'll check it with an easy case first. So let's say f of x equals x cubed and g of x equals the cube root of x, and we'll say, are they inverses? Or we may say, is g the inverse of x? That would be another way that we could have this problem stated, is g the inverse of x? So we're going to check what is f composed of g of x. We'll check that first. This is f of g of x. In this case, g of x is the cube root of x. So if you remember how composition works, this is from section 2.8. We take the f of x function, we replace its x value with the cube root of x. So instead of getting x cubed, the cube root of x, what was right here, replaces the x up here, and we get the cube root of x cubed. Well, the cube will cancel the cube root, and it goes down to just x, which that's what we wanted to happen if they are inverses. F composed of g of x equals x. We just shows that f composed of g of x simplifies down to x for these two functions. So we need to check the reverse order now, because you have to check both of them. This is what about g of f of x? So that's g of f of x is x cubed. This now says take the x value in the g function, it was cube root of x, replace the x with x cubed, so we get the cube root of x cubed, which is just x. So in this case, yes, they are inverses. And we could say g of x is equal to the inverse of f of x. So g of x is actually the inverse. So yes, we showed that the two equations go down to just x, so these two functions are each other's inverse. We're going to do one more of those types, and then we'll look at a couple things to wrap up stuff. So for this example, we're going to say f of x is equal to negative 2x plus 8, and g of x is equal to negative 1/2 x minus 8. And we'll say, is g of x the inverse of f of x? So we're checking the same thing we did in the previous problem. It's asking it a slightly different way, but it's asking us to do the same thing. You have two functions. You want to check, is g the inverse of f? So we got to check, what is f composed of g of x? Is that just x? This is f of g of x is f of g of x. So this is the f function evaluated at g of x is really negative 1/2 x minus 8. So this says go to the f function where the negative 2 was in the f function, where the x was, replace it with this stuff here. So the x is being replaced with negative 1/2 x minus 8. And we can say, all right, what's this going to simplify down to? We distribute the negative 2. Negative 2 times negative 1/2 is positive 1, so we just get positive 1x. Negative 2 times negative 8 is positive 16 plus 8, so I get x plus, 24? And so in this case, no, it doesn't work out. We don't get just x back from these two problems. You get back x plus 24, and since we got back something other than just x, in this particular case, these are not inverses of each other. Okay, so moving on. Let's see, let's do one more type here. So the final types, the last couple group of questions that you guys will see in the assignment is they give you guys an expression. They want you to find the inverse if it's 1-to-1. They want you to graph it and its inverse in the same axes. And then they want you to list the domain and range of the expression. So this next couple examples we do here will be similar to the last groups of problems you guys will see. So let's say that they give us y equals 2x plus 3. And they want us to say, first of all, is this 1-to-1? So this is a diagonal line. It's a diagonal line, so yes, it's 1-to-1. So we can proceed and find the inverse. If this was not 1-to-1, then like it was absolute value that has the V shape, so a horizontal line will hit it twice, then we say no, it's not 1-to-1, so there is no inverse to find. All right, so we say, is it 1-to-1? Yes. And then we want to find f inverse of x. So we said, all right, replace the symbol f of x with y. It's already kind of done for us with this equation. So what we're going to do now is switch the x and y. And we're going to solve for y. So the 3 subtracts across. And then I need to divide everybody by 2. So x over 2 minus 3 over 2 is my y. So my inverse function f inverse of x is equal to x over 2 minus 3 over 2. So we got our starting value. We verified it was 1-to-1, so it's invertible. We just found the inverse using the switch x and y trick. Now they want us to graph the function and the inverse in the same axes. And so I'll do f of x in kind of this bluish color, and I'll do f inverse of x in sort of this greenish color. So when you guys want to graph a function and its inverse, f of x, our function here to start out with, it's a y-intercept of 3, and then it's a slope of 2, so every time it goes up 2, it goes to the right 1, and that gets another dot that we know the line passes through. So this is our f of x. When you guys want to graph the inverse, what you do is you draw in the diagonal line y equals x. So you draw in the diagonal line y equals x. And you reflect the original graph about that line. So if the original graph has a y-intercept of 3, when you reflect it about the graph, that becomes an x-intercept of 3. Any point where the original line crosses this dotted line, the dotted line y equals x, the inverse will cross there as well. And this would be the graph of our inverse. So basically, if you guys are given the graph, we'll do another example of this graphing type. So if you guys are given a graph and you want to find the inverse, you draw in the diagonal line y equals x, and you take the reflection of the original line about that diagonal line. So we get this right here is our graph. So that's the graph that a lot of these problems are going to ask you for. That's our graph. And then the final thing that these types of problems ask you is what's the domain and range? Well, since y is a diagonal line, the domain of domain of our original function and the range of our original function, since the original function is a diagonal line, the domain of f of x is negative infinity to infinity. If you remember, domain of a diagonal line is all real numbers, and the range of a diagonal line is also all real numbers. Well, if we remembered what we said about the domain and range, how they're related, let's back up here. The domain of the original function is the range of the inverse, and the domain of the inverse is the range of the original function. So we know the domain of the original function, so we know what the range of the inverse equals. We also know the range of the original function, so we know what the domain of the inverse equals. So the domain of f of x is this, and then that equals the range of the inverse, and the range of f of x is that, so that will equal the domain of the inverse. So the range of the inverse is all real numbers because that's what the domain of the original is. The domain of the inverse is all real numbers because that's what the range of the original is. So you guys will have some problems like that towards the end of the assignment. If you guys get a type where there's like one of the types, maybe something like, say, f of x equals x squared minus 4, and they want you to say, is it 1 to 1? If so, find the inverse, graph it, and domain and range. So that'll be something like, if 1 to 1, find f inverse. Then it'll say something about graph f and f inverse, and then it'll want to know domain and range of f and f inverse. Well, this is a parabola. It's a parabola shifted down 4. So we know that it's going to fail the horizontal line test. I can find a horizontal line that'll hit it twice. So this fails horizontal line test. So it's not 1 to 1. So there is no inverse. In the assignment, there's like a little 2 kind of circle things. Look for the one that says part B, that says there's no inverse, something like that. When I looked through the homework things, it was a little kind of weird the way it's phrased. But any of them that fail to be the horizontal line test, you have kind of a choice A and B, and if you fill out choice A, it starts doing some more stuff. But if there is no inverse, kind of just say, okay, well, there's no inverse. It's not 1 to 1, so there is no inverse, so you just go with choice B. So to wrap up, I'm going to do one more of those graph types, and then we'll do one last one last type where you are given two functions and asked if they're each other's inverse. So let's say that we have a function f of x, and let's say it's a cubic function that's shifted up 2. So we have kind of a graph like that, and we want to graph, I use a different color, we want to graph f inverse of x. So what we said to do in the previous problem, first of all, this is 1-to-1. Every horizontal line only hits it once. So we're good to go there. We draw in the diagonal line y equals x. And then once we have the diagonal line y equals x in, we'll reflect the original graph over that. The original graph had a y-intercept of 2. That's going to become an x-intercept of 2. The original graph kind of curves closer to the line, then back out. So the inverse curves closer to that diagonal line, then back out. We know it's going to have to clip through here. We kind of head outwards, then inwards. So we head outwards, then inwards, and then it continues on through, and we continue on through. So we get the mirror image of the original function about this diagonal line y equals x generates the inverses graph. So when you graph them, that's basically how you do it. And we said, to wrap up, final thing, let's say that we had two functions and we want to know if they are each other's inverse. Let's do one more of those type. Give me just a second to generate two functions. So let's look at what if f of x is equal to x cubed minus 1 and g of x is equal to the cube root of x plus 1. And we want to say, is g of x the inverse of f? So we got to check what's f composed of g of x. That would equal f of g of x. That would equal f of the cube root of x plus 1, which says go to the f function, replace the x value here with the cube root of x plus 1. So instead of x cubed minus 1, which is the f function, we created a spot where the x used to be, and we're going to put the whole g of x, cube root of x plus 1 in there. The cube cancels the cube root, so you get x plus 1 minus 1. Plus 1 minus 1 cancel, so we just get x. So far that's good. F of g of x goes down to just x. That's what we wanted. And then we want, what about g of f of x? This is g evaluated at the f of x function. This will be g evaluated at x cubed minus 1. So I'm going to go to the g function, and I'm going to create a spot in the g function to put the x cubed minus 1. So I put the x cubed minus 1 there. Minus 1 plus 1 cancel. When you take the cube root of x cubed, that goes down to just x as well. So in this case, yes, the g of x function is the inverse of f of x, and we could write the g of x function is actually equal to f inverse of x. So the types of problems you guys see, stuff asking you guys in the assignment for is things 1-to-1, use horizontal line test. If they give you guys one function and ask you guys to generate the inverse, switch x and y, and then solve for y, and that's the inverse. If they give you guys two functions and they say, are they, is g the inverse of f, or are they each other's inverses? Then you guys go through this process we just did right here. Check what's f composed of g of x and what's g composed of f of x. Make sure they go down to just x. If they go down to anything else, then that's not g is not an inverse of f, or they're not each other's inverse if you get stuff back other than just x. The last types that you guys have in the assignment is they give you a function, they ask you is it 1-to-1. They say if it is 1-to-1, find the inverse. So to find the inverse, switch the x and y, then graph it. To graph it, graph the original function, put the dotted line, and then reflect about the dotted line to get the inverse. And then they want to know sometimes what's the domain and range. So figure out the domain and range of the original function. The domain of the original function is the range of the inverse, and the range of the original function will be the domain of the inverse. And just kind of remember, if it's type that's not fails a horizontal line test, there is a choice B kind of there where you just say, hey, there is no inverse, and they have an option, kind of an option like that for those types. That's basically everything you guys should see in the section. So we'll just wrap it up there.